And thanks for having me today. Um, as Chris mentioned, I'm going to go over a little bit of background and then computational design at Stantec kind of in general, and then go over two case studies. One is a tool, and then one is more of a bespoke kind of comprehensive design solution. So a little bit about myself. As Chris mentioned, I'm the global computational design lead within buildings for Stantec. I'm an architect and a structural engineering designer. Some of my background, I was actually born on an Air Force base in North Dakota. And from there, moved around a bunch all over the country. Didn't end up in Detroit though. And then went to Texas Tech for my undergrad, where I got a Bachelor of Science in Architecture and a Bachelor of Science in Civil Engineering with a mathematics minor. Where I really started to focus on using computational design to develop both structural and architectural solutions to the design challenges. Went to Virginia Tech to get Master of Architecture, started integrating with more different disciplines, and getting some kind of experience working with international teams. From there, I went to Beyer Blinder Bell and worked on both kind of historic projects and also some complex computational design work. Some of these are, on the top right, the Planet Word Museum. You can go there and see the layout of the entire kind of development of language and written word. These characters are embedded in the terrazzo in the lobby there. Also the gate. Some of the more confidential work involves the Pentagon, doing survey work there, and also the Statue of Liberty. From there, I went to Smith Group in DC, where I worked on a lot of cultural projects, museums, incorporating kind of the data analytics from the existing collection to help inform the design of future collection kind of layout and storage requirements, in addition to other work. Then I went to San Francisco, working still at Smith Group at that time, working on healthcare projects. This is a hospital tower where we ended up having the opportunity to design this breezeway soffit condition as well, which is all FRP. And from there, I joined Stantec in this new role as the Global Computational Design Lead, which is within design computing, a new division that we've created. So going on kind of a little bit of an overview of Stantec, mostly both from the website. There's over 34,000 employees at 450 plus locations on 6 continents. And one of the benefits that really gives us in terms of our work is this ability to collaborate internally with different discipline experts. And I'll kind of dive into that a little bit more later on in terms of the comprehensive design solutions that we're developing and what that kind of allows us to do. So a question I get a lot from different people is like, why computational design? And we'll get into what it is too, for those that maybe aren't as familiar. But one of the goals that Stantec has in buildings is to build the world's leading integrated design practice driven by their commitment to performance by design. And what computational design really gives us is the ability to use data and performance metrics to define the design solution. And why that's important is these design challenges are becoming more complex. The speed to deliver is becoming faster. There's this ability to rapidly adapt to different changing requirements or constraints that might come up as the project develops. And we also need more comprehensive solutions. And there's limited capability within traditional workflows. So that's kind of hindering some of the work we're trying to do. And what's enabling this is the ability to do rapid custom component fabrication, modular construction, and then along with faster computing power. So a little bit about what is computational design. I've heard lots of different definitions. People try to define what it is. I think this definition somewhat fits and is useful for what I've seen so far. So using algorithms, data, and digital tools to enhance the design process. And that really allows us to transform the way we approach those design challenges. So a quick example on the right is taking this table from NFPA, which deals with the sprinkler spray clearances and those requirements for no obstructions within those zones, and converting that into just a simple component within Grasshopper, we can use that to define those clearance areas around the sprinklers, update the geometry to make sure that we're not clashing, or move the sprinklers or align different elements of the design to fit that. So we're getting instant design feedback, even related to code requirements or design direction. And so these are some of the basic tools. I think it was interesting what Chris was mentioning too about being somewhat tool agnostic, in that you don't want to limit yourself to what a few software. A lot of this is more about a process. These are potentially the main tools that we work with in the industry that I've seen so far, that most people I believe I've also seen. As Chris was mentioning, Excel and Rhino Inside are very critical to the work that we do in terms of incorporating data into the design process and linking both geometry from more flexible design solutions in Rhino over into Revit. And obviously, Python and other coding platforms, but Grasshopper and Dynamo as visual programming allow us quick access for designers and engineers to get into, and architects to get into coding. So as I mentioned, it's less about the tools, but a lot about the mindset and how you're approaching the design challenge. So computational design really involves designing systems that allow for iteration, feedback, and optimization. There's the ability to have some reproducibility if we want to change anything, and the transparency in the decision making. This is how this data is being used to modify the design, and obviously allow for some cross-disciplinary collaboration, which we'll get into more with the comprehensive design challenges that we approach. And then just some images on the slide there of that. So some more kind of applications in practice. I'm sure a lot of you have seen some of these applied on projects in your own work: facade optimization, space planning and adjacency analysis, environmental and daylight performance modeling, structural fabrication and rationalization, automation of documentation, and then visualization and communication of data. But yeah, a lot of this is about driving performance in the design by having access to the data and being able to actually use it effectively to drive design solutions. So at Stantec, we have kind of two different overarching, within buildings specifically here, two overarching sides to this. There's the digital practice side, and then there's the design computing side. So digital practice is more on the delivery and documentation side, whereas design computing, where we have located computational design, is more on the design side, working directly with designers on integrating the data into the design process and delivering these complex solutions. Locally, we have tech teams at every business center or office that are really implementing this on local projects, and then having access to additional resources as necessary. So that's a little bit about the structure. How we keep in touch and how we build this network. Obviously, there's over 34,000 people at Stantec. A lot of different business lines, but within buildings even, there's more than 6,000 or 7,000 people. So we hold these regularly scheduled kind of meetings. The computational design peer-to-peer calls are more kind of presentations that we give. We invite outside speakers or inside speakers to come. And this is held most likely about every month. But then we also have these computational design work sessions where we have people just pull up whatever they're working on and share and get feedback. So we have that community and that network, so we can all keep in touch and help each other. So the main way that we approach computational design, there's kind of two different approaches: that creating a tool that'll be applied on multiple projects, and then more the bespoke kind of comprehensive design solution, where we incorporate the constraints of the actual project into this script. So the tool example, the case study I was going to give here, is actually the one Chris mentioned that we just won the award for, the Collaborative for High Performance Schools View Analysis. And this tool is designed and developed in order to assist project teams with determining essentially where they need to add windows to meet the view credit requirement. So within these schools, there's this the credit for the high performance schools, they have these requirements in order to create views for the students. So the actual contributing area of the window is 2.5 feet above the floor to up to 7.5 feet above the floor. And then they also are wanting to calculate the width of the window. So it's pretty specific in terms of something that we could code into a script and get that information out. So the way this script works is we're pulling the Revit model as it's already been developed. So we're using Rhino inside to pull the geometry, the doors, the windows, the curtain walls, and obviously the rooms. Running the analysis to pull out the assign the rooms to the windows to the rooms, and then calculate the width, and then visualize that output in both a graphical form to get some quick design feedback, and then also to export an Excel document that can be used to report for the credit. Some example of that input, here's pulling some of those rooms. So if there's two adjacent rooms and the windows are in between those rooms, then this window would be excluded. A quick kind of example of how the script can kind of automate some of that. And then it assigns the exterior windows to the rooms so that we can calculate those areas. And there's a little bit of manual input on the front end here. So you can have the designer select, which curtain wall components, they might not be named or labeled properly on the front end by the design team. But during this process, you can easily go through and select which ones you want to make sure they're contributing to this. A little bit of that overview here. This is basically the output that you're getting within the Rhino window. So this kind of updates live as there's changes. So in the red, we're able to quickly see which rooms don't have windows or don't have enough windows. You can see in blue, and yellow, there's some that are somewhat meeting those requirements, having some windows, but not enough to meet the full credit. And then in blue, those are the rooms that are already performing as much as they can. There's a limit to the amount of glazing that can contribute to this credit. So just a little sample of what that looks like in the viewer. So designers are able to look at this and quickly check, okay, each window and each room is actually being counted properly, and we're getting those the calculation properly for that credit. So part of what one guy on our team, Jivitesh, added into this script is the ability to jump room by room as well. So someone could go back and do a quick check to make sure that each room is pulling the correct amount of the right windows and assigning the right areas. Pull that in. And then on the kind of back end, on the exporting side, this exports all the Excel data that would be submitted for the credit. And you can see on the bottom right, there's kind of a percentage that allows for certain points. So in this case, this is a real world project that it was run on, that we're almost to getting the second point on this credit. And so you could quickly decide, it's worth it for the client to go back in and add additional windows at certain locations in order to meet that credit. So really this is to help inform the design decision process as the project develops through each phase. And some of those results, so far this has been applied on at least 3 or 4 projects, which has resulted in quite a lot of savings in time. So to manually run this, originally on a project of that scale, it would take about 20 hours for someone to go room by room, measure the windows, and then go back and check that and assign those values. And very likely there was some level of error in that that already existed. So this script kind of takes away some of that potential for manual errors while also speeding up the process considerably. And by adding in that ability to jump room by room and do a double check, that can kind of catch any of those issues that might pop up from the script not potentially reading the geometry correctly, or if there's something that was encoded in the Revit model improperly, or sometimes people model things not according to the standards. So this allows people to do that quick double check while also making sure that you're getting quality results. So yeah, on this project in particular, it took about a little over 110 hours, about 110 hours to develop the tool, which on one of these projects alone, it would have taken probably 60 hours of manual work to do, but this can now be applied on multiple projects as it already has. So it already saved considerable amount of effort from the team. And I was going to take a pause here and ask questions. The next case study we'll probably have to not record. But did anyone have any questions in particular on this case study?
Native Revit not capable of that caused you to go to outside additional programming?
Did you catch that, Cooper?
It sounded like you're questioning if you'd want to do it maybe in Dynamo or just directly and natively in Revit. Is that right?
Yeah, I don't know if Windows could be associated with rooms in Revit, but yeah, why expand beyond Dynamo?
Yeah, so Dynamo, from my experience, the geometric capabilities are somewhat limited. It runs much slower. Rhino and Grasshopper in this case, I think, give us the capability to run this at a much faster speed and kind of dive into the data a little closer, since the Rhino window allows for more, I think, graphical display than Dynamo. For the most part, I don't use Dynamo as much for anything related to geometry or even data analytics for that part, and use Dynamo mostly for sheet creation and documentation efforts. So it might have been driven a little bit. I'm not sure you can also do this in Dynamo, but it might also have been driven a little bit by my preference to work within Grasshopper, which from my own experience has higher capability in working with high levels of complex geometry and data.
Thank you.
I think we're going to keep going.
Okay, great. Yeah, so the next case study I wanted to present on was this comprehensive design kind of solution, these bespoke solutions. This example here, this image was from that hospital project for the breezeway soffit, which is all FRP panels. But really what kind of drives this is this fragmentation of building design expertise. So I've seen this on a lot of projects, or now in modern times, that master builder and craftsman, there was kind of this level of skill across the entire thing that's been lost because of the increasing building complexity, increasing contractual obligations. So there's this loss of craft and then also loss of building knowledge and all of these sub-disciplines and all of these subcontractors that have come out of this. So there's kind of this extreme level of expertise that's needed that really has fragmented how we approach designing buildings. And even, in school and in the profession, you see this a lot. There's this kind of disciplinary drift between architects and engineers. We're speaking somewhat different languages where there's loss of communication, there's lost information between why we're doing something that we're doing, and what are other potential options. So the way I've kind of seen it done is there's this multidisciplinary approach, which is similar to like working in CAD, where you send something over the fence and people react and adjust and modify to that. And that's kind of how it was done before. And now we're kind of in this more interdisciplinary approach, which is in BIM, where everyone's working in the same model, but you don't know why or how, or well, kind of how, but you don't know why, necessarily each team has designed a system the way that they have. So kind of this newer approach is kind of this transdisciplinary approach where you could work in a centralized Grasshopper model and encode the kind of the why and the reasons why your design is taking on a certain effect, so that each team can react and be more participatory in the actual development of the design. So contributing their performance metrics into that design process to help drive the design instead of react to what each team is doing. And so the way that kind of works in this case study, this previous case study, at this hospital, the breezeway, the soffit. So we had, this initial idea that's shown a little bit on the left with this confluence, this flowing of rivers that came into kind of a conceptual diagram rendering. And as the project developed, we can continue to build in different requirements. The code requirements, as I mentioned, sprinklers, the spray clearance, making sure that the form actually adapts to that. The edge conditions might change. And then also engineering requirements in terms of panel size, fabrication, the thickness of the material, the tolerances that are required, and then the client requirements in terms of operational cleaning and maintenance, and so all these things can continue to be overlaid into the design as it develops. And so even though we don't know it all at the beginning, you can go back and modify the geometry for every single panel that's unique. And so the way I've seen this work on a lot of firms is you have kind of this disconnect both between the architect and the computational designer, but then also between, the internal computational design model, if you have one, and the external consultants if they have one. So there's kind of two levels of a loss of information. And ideally, both teams are working in the same model. So there's someone taking that discipline expertise and encoding it into a computational design model that is informing each other. But ideally, you also then have computational design architects and computational discipline experts who are encoding their own expertise into the centralized model and modifying the data and the geometry according to their expertise and what they bring to the table. So some of those necessary skills for this kind of new role as a transdisciplinary computational designer is computational design thinking, breaking kind of these complex ideas down to simple, an understanding of 4D space, the geometry and installation sequencing, materials and fabrication constraints, and the level of detail required, how to script that discipline expertise into the computational models, bridging models and working in that comprehensive design space. So how do we, react to each other in that team? And then the mindset of collaborative design, which is really critical, that everyone's an active participant and not just reacting to something that you've seen. So it takes a little bit more of, I think, an understanding of what each team is working on, which takes a little more effort. But I think in this way, the design actually develops according to the actual project constraints and requirements instead of, what we did on the past project.